It is my great pleasure today to host Professor Tim Roughgarden, who is a professor at Stanford University. Tim has a distinguished career as a great researcher and superb teacher, working on algorithms and more specifically, primarily interested in algorithmic game theory. He has written a number of books, and he has taught a MOOC, I believe, and he's great.
Okay, thank you, Professor Mathieu. Bonjour, thank you for coming, everyone. I've spoken in this room once before, a little more than 5 years ago. It's a pleasure and a privilege to be back. My goal for today is to introduce you to a few of the many points of contact between two fields, computer science and game theory. So what do these two fields have to do with each other? So let's go back to the beginning. The beginning is in the early part of the 20th century, when a single individual actually made really important contributions to the early development of both of these fields, that individual being John von Neumann, widely regarded as one of the most important mathematicians of the 20th century. So back in the 1920s, von Neumann had already laid the groundwork for what would become the field of game theory, but the field only sort of started having a lot of influence. It only went viral when von Neumann wrote his book with Oscar Morgenstern in the mid-40s, Theory of Games and Economic Behavior. And kind of amazingly, it was just a year later when von Neumann started helping with some of the world's first ever general purpose computing devices, initially as an advisor with the ENIAC project, and then leading an effort at the Institute for Advanced Studies. Okay, so kind of amazing CV, especially that these were happening at roughly the same time. Despite that, as far as I know, von Neumann never thought about connecting these two projects of his. He worked independently on game theory and on issues of computing. And indeed, as the 20th century unfolded, these two fields developed kind of just totally in parallel, with very little communication between them. And that's a big contrast to the 21st century, where there's been a really lively conversation between the two, which is what I want to tell you about today. But before I skip to the 21st century, I want to spend a little more time in the 20th one, looking at one revolutionary idea from each of these two fields. So let's start with game theory and the concept of a Nash equilibrium. So in 1950, John Nash proved an amazing result, which in some sense gave game theorists and economic analysts everything they might possibly want, a guaranteed universal existence theorem. So Nash's theorem says that in any strategic situation whatsoever, doesn't matter who the participants are, doesn't matter what they can do, doesn't matter what they want, there's always going to be at least one, what Nash called an equilibrium point, what we today would call a Nash equilibrium. And the reason this is, what you'd really want as an economic analyst is it says that, with no extra assumptions, no matter what strategic situation you're talking about, you can always reason about your application using these equilibria, which are guaranteed to exist. All right, so what is a Nash equilibrium really? Well, I think you probably all have a quite sort of strong and intuitive idea of what an equilibrium is. You have a bunch of actors, and basically at an equilibrium point, nobody wants to move. Everybody's happy doing what they're doing, given what everybody else is doing. Okay? Hopefully you don't think you know what a Nash equilibrium is because you watched the film A Beautiful Mind, because the key scene in that film, which purports to explain the concept, actually gets it completely wrong. So if you've ever seen that, please just wipe it from your memory. So the best way to get a better feel for Nash equilibria is to look at some examples. So for example, you can think about the game of chicken. Okay? So there's two drivers driving at each other at full speed. And each one can either swerve or keep going straight. All right? And the goal in chicken, the way you win in chicken is, well, first of all, you don't want to get into an accident. That would be really bad. But you want the reason you didn't get into an accident to be because the other person chickened out. You went straight and they swerved. So we can summarize that situation with a 2x2 matrix, okay, where the rows correspond to the possible actions of the first driver and the columns to those of the second driver. In each entry, it shows the payoffs of the row and column player respectively in that outcome, with higher payoffs being better. So you can see that if they both go straight, then they get into an accident. They both get negative payoffs. and if one of them swerves and the other's the chicken, let's say the winner gets a payoff of 1 and the chicken gets a payoff of 0. Okay? So that's one way to express the incentives in the chicken game. And it's not hard to see that there are equilibrium points of the chicken game. For example, you can imagine that the first driver chickens out and the second driver just goes straight. That's going to be an equilibrium. Obviously, the second driver is happy because they won the game. Okay? The first driver, while not that excited about having been the chicken, if you look at their alternative, that would be to go straight and get into an accident, which would be even worse. So the first driver is also satisfied with its outcome given what the other driver is doing. So that would be one example of a Nash equilibrium. There's a second one with the roles of the players reversed. Another familiar example would be rock, paper, scissors, or Rochambeau. So I think you all know the rules, right? So paper covers rock, rock smashes scissors, scissors cuts paper. So this again, we can summarize as a matrix, this time a 3x3 matrix, because each of the two players has 3 available actions. If there's a draw and they pick the same action, then they both get payoff 0. Otherwise, the winner gets a payoff of 1 and the loser a payoff of -1. Now, you may have trouble reconciling the statement of Nash's theorem with the example of rock, paper, scissors. Because actually, if you think about it, none of these 9 outcomes constitute a Nash equilibrium. In every one of these outcomes, one of the two players would want to switch. For example, if player 1 picked scissors and got smashed by rock, player 1 would not be happy at this outcome and would want to switch to paper to cover rock. Same thing true in the other 8 outcomes. So what's important to know about Nash equilibria, the twist, is that players are allowed to randomize. They're allowed to flip coins in their mind and use the outcomes of those coin flips to decide which action they want to take. And once you allow randomization, rock, paper, scissors does have a Nash equilibrium. It's where each of the two players are just choosing an action equally likely, uniformly at random. The reason that's a Nash equilibrium is because if you randomize uniformly, it guarantees that no matter what the other player does, you're equally likely to win or lose or tie. Okay? So the content of Nash's theorem is the statement that the fact that we can identify these equilibrium points, it's not special to these simple examples of chicken and rock, paper, scissors. It doesn't matter how many dimensions your matrix has, how many players you have. Doesn't matter how big it is. Doesn't matter what numbers are inside. In all cases, there's at least one way for players to randomize so that nobody wants to switch. Okay? There's always at least one Nash equilibrium. Okay? So that's cool. So game theory gives you some advice about how to play rock, paper, scissors. It's just flip some coins in your head and then choose randomly. And you should consider that strategy as a fallback, if nothing else. And there's the problem that it's kind of easier said than done. Turns out people are really bad at flipping independent random coins in their head. Okay? And I sort of know of no better example of this fact than if you watch the World Championships of rock, paper, scissors. You did know, right, that there was a World Championships of rock, paper, scissors? $50,000 top prize. So indeed, I encourage you to check out the clips on YouTube if you haven't seen them. You will see just how impossible it is for humans to avoid predictable patterns. Okay, so moving on to computer science and rewinding a little bit back to 1936. That was the year that Alan Turing wrote the paper that many computer scientists view as the birth of our discipline. Okay? And for this reason, many of us think that Alan Turing's name should be as widely recognized as, say, Albert Einstein. So what made Turing's paper so important? Well, so 2 things. First, he introduced a formal mathematical model of exactly what it is general-purpose computing devices are capable of. This is a model we would now call the Turing machine. So this is a model of what computers can do. Now, mind you, this is in the mid-1930s, a full 10 years before anyone would actually build a general-purpose computing device. So Turing gave us a theory of computing before we even had computing in the modern sense of the word. So that's pretty amazing. The second thing you should know about Turing's paper and why it's so important is that once you have a model for what it is that computers can do, you can start speaking about what computers cannot do. And in this very first paper of Turing's, same paper, he showed that there are so-called undecidable problems, problems that will never, ever, not in 2018, not in 3018, never be solved in general by a computer. Okay? And some of these are actually quite natural, things you might want to solve, like the halting problem is a famous example. That just says I give you a program, say 1,000 lines of Python, and I just want to know whether or not that program is going to loop forever, or whether it's eventually going to halt. So you could try to just simulate the program, but then the obvious problem is, if it runs for 100 years, how do you know if it's in an infinite loop or if it's going to terminate tomorrow? Okay? You might hope that there would be some clever shortcut that allows you to quickly just figure out the answer, but Turing's theory says that there isn't. So I talked about how Nash's theorem in some sense gave economists and game theorists everything that they might want, universal existence. The experience for computer scientists has been rather different. Literally since the birth of our discipline, we have known that we can't always get what we want. There are problems that will never be solved by computer. So I don't know what you think of when you think of the name Alan Turing, but I often think of the Rolling Stones because of their song, "You Can't Always Get What You Want," which sort of summarizes the experience of a computer scientist pretty aptly. Okay, so in the rest of the talk, what I want to do is discuss 3 case studies of 21st century research which is happening on the boundary of these 2 fields, computer science and game theory. The first case study, on the one hand, it's about a model which is near and dear to my heart, but at the same time, I think it remains one of the most vivid illustrations of why computer scientists and game theorists really had to start talking to each other. It was really inevitable that they would start joining forces. So this is a model about routing traffic through a network. Now, when a computer scientist is thinking about routing problems, usually what they have in mind is data flowing through a communication network. But for the purposes of today, I encourage you to think about something with which you're probably all too familiar, namely vehicular traffic on road networks. The principles are largely the same. So let me introduce you to this model with an example. It's a very old model, almost 100 years old, discussed by A.C. Pigou in his book, The Economics of Welfare. And so here's the example. All right? So at the moment, I'm on sabbatical in London, but normally I live in San Francisco, California. And I work at Stanford University. And it turns out there's 2 highways that connect San Francisco to Stanford. One is called Highway 101, the other is Highway 280. So which one should you take? Well, if it's in the middle of the night, if it's like 4 in the morning, you definitely want to take Highway 101 because it's shorter and you'll get there faster. In the middle of the day, it's less clear because Highway 101 is more prone to congestion, more prone to traffic jams. So on this slide, I'm showing you a caricature of that situation. So think of S as San Francisco and T as Stanford. Here are our 2 highways. Each is annotated with what I'm going to call a cost function. So C of X, it just means the travel time incurred by traffic on that road as a function of the fraction X of traffic that chooses to use it. So the bottom road is a caricature of Highway 280. This is something with no congestion at all. Doesn't matter if it's empty, doesn't matter if it's full. This always takes 1 hour. This is a caricature of Highway 101. It gets congested. Let's say the travel time in hours is equal to the fraction X of traffic that chooses to use it. So if this is fully congested, if everybody uses it, it takes an hour. If only half the traffic are using it, it would only take that traffic 30 minutes. Okay? So what I want to do next is ask 2 questions about Pigou's example. Question 1, what do we expect to happen? What do we expect drivers to do, assuming naturally that they just want to get to their destination as quickly as possible? Question 2 is, if hypothetically we had complete control over everybody's routes, would that allow us to improve over the selfish outcome, the equilibrium outcome? So let's start with the first question. What do we expect drivers to do in Pigou's example? Well, actually, I've set up the problem so this is a really easy question to answer. In game theory parlance, you would say that every driver has what's called a dominant strategy, a strategy which you always want to do no matter what others are doing. That's because the best case scenario on the bottom route, 1 hour, is no better than the worst case scenario on the top route. Okay, so it's sort of a no-brainer to take the top route. You can only be better than as if you were on the bottom route. So that means at equilibrium, we expect to see all the drivers on the top route. It's fully congested, and it takes them all an hour to get from S to T. Question 2, could we do better if hypothetically we could choose routes for people? Well, if you play with this example for a while, you realize that actually pretty much anything would be better than this equilibrium. If you happen to be an altruistic dictator, you would be wise to dictate a 50-50 split of the traffic. So it's true that half of the traffic is now stuck on this bottom route. It takes them an hour just like before. But the half, which is still on the top route, they now enjoy a relatively uncongested ride. And they get to T in only 30 minutes. So that means the average commute time has dropped from 60 minutes down to 45 minutes in this 50-50 split. Okay? So this demonstrates something probably we could have guessed, which is if you just let people do whatever they want, the outcome is not necessarily the same as the best outcome for society. What's going on here is what an economist would call a congestion externality. As a driver, when you choose your route, you're thinking only about your own travel time. You're not taking into account the fact that your presence makes everybody else on those roads get there a little bit slower. Okay? So because of that externality, you see this difference between the quality of equilibrium outcomes and socially optimal outcomes. So Koutsoupis and Papadimitriou introduced a notion of the price of anarchy, as they called it, which is a measure of just how bad it is when you let people do whatever they want. Okay, so how much worse is the equilibrium outcome compared to what you could attain hypothetically with full centralized control? So it's just the ratio of an equilibrium to the ratio of an optimal solution. So in Pigu's example, this ratio would be 60 over 45. We had 60 minutes in the equilibrium, 45 in this optimal solution, also known as 4 over 3. Okay? So that's the price of anarchy in Pigu's example. Now, Pigu's example is not the most famous example of this routing network. That distinction belongs to something known as Brace's paradox. And this is a nice example to know. Comes in handy at like cocktail parties. Well, at least sufficiently nerdy cocktail parties. Okay? So, Brace's paradox, we again have an S and a T, and we again have two routes. Each of the routes comprises two edges. One edge that's like Highway 280, a 1, and another edge which is an X. Okay, 1 and X mean the same thing as on the last slide. So in this network, the two routes are equivalent. So what you'd expect to have happen in equilibrium is you'd expect traffic to split 50-50 between them. That would equalize the commute time along each at 90 minutes. So that seems kind of boring. It doesn't really seem like a paradox. So the paradox comes in when somebody announces a new invention, a teleportation device. And when you install a teleporter at the midpoint of this top route, allowing you to go instantaneously to the midpoint of the bottom route. Okay? So what's going to happen now that we have this teleporter? Well, all of the drivers want to use it. Right? So like if you were the first driver to switch from the red traffic pattern to using the teleporter, your commute time would drop from 90 to 30 plus 0 plus 30, which would be 60. Okay, so it's a no-brainer to use the teleporter. Turns out that's true no matter what other players do. This, again, is a dominant strategy. So at equilibrium, everybody makes use of the teleporter, and in their haste of doing so, the upper left and lower right edges wind up being fully congested. So they now each take an hour of travel time, and the commute time of the traffic has actually gone up from 90 minutes to 120. So this is the paradox. If you have full control over a network, making the network better can only make the outcome better, can only make the traffic routing better. But if routes are chosen by self-interested agents, self-interested drivers, network improvements can actually lead to worse outcomes for everybody. Therein lies the paradox. Now, I don't want you to think that Brace's paradox is just some artifact of some specific model of traffic routing. It's actually a very fundamental sort of concept that shows up in many different guises. For example, it shows up in various types of physical systems. So one way of realizing it is you can take a bunch of elastic springs, and you can take a bunch of inelastic strings, and you can tie the strings and springs together in sort of a network or a contraption. like I've shown on the slide. And I want you to think about taking this network of strings and springs and attaching one end of it to some heavy base, like to the bottom of a table, like this. And from the other end, you're going to hang some heavy weights, which of course stretches out both the strings and the springs. Now, if you build it just so, if you build it like shown on the slide, it's actually the case that if you take a pair of scissors and cut a taut string from the middle of that network, despite the fact, you're cutting up this thing, it seems like you're just making it weaker and weaker, you cut this taut string and the weight actually levitates further off of the ground. And there's a couple ways you can see this. One is just through analogy with our traffic routing networks. You can realize that the same equations that govern the physical position of these strings and springs networks are the ones that govern the traffic equilibria in the routing network that we're thinking about. So here, force corresponds to traffic flow, distance corresponds to travel time, the elastic springs correspond to the x's, the inelastic strings correspond to the ones and zeros. So by cutting this taut string, we're doing nothing more than removing the teleportation device in order to recover the superior equilibrium in the original network. Okay? So that's one way. You can also see it sort of directly physically on the slide, which is that what's going on is severing the taut string frees up the two springs to carry the weight in parallel rather than in series. And as a result, they are not stretched out as far. Okay? And this isn't just theoretical. You really can build this contraption and exhibit this levitation. At some point, maybe 5 years ago, I really wanted people to be able to go on YouTube and search for Brace's paradox and get these dramatic clips of this levitation happening. So what do you think I did? You think I built one? Nah. I signed it for extra credit in my graduate course. So now, if you search on Brace's paradox on YouTube, you can see the fruits of those students' labor. You do see some actual demonstrations of this fact. Okay, so let's take stock of where we are. We have this routing network. We've looked at two examples. Pigu's example, remember the price of anarchy was 4/3 here, 60 divided by 45. We saw Brace's paradox, and I forgot to mention, Brace's paradox is a second example of a network where the price of anarchy is 4/3. So the equilibrium here, remember everybody was on the zigzag, and that was a commute time of 120 minutes. It turns out the socially optimal thing to do is ignore the teleporter and go back to the 50-50 split, which gives you a commute time of 90 minutes. So the price of anarchy in this network is 120/90, or again, 4/3. So we've seen two examples. In both, there's a 33% loss from selfish behavior. And if you were feeling sort of really bold, delusional maybe even, you might be tempted to conjecture that, maybe this is always true. Maybe the price of anarchy is actually never more than 4/3. And the reason that's such a bold conjecture is that networks can get much bigger and much more complicated than these toy networks that we see in these two examples. But despite being, seemingly a little, delusionary, it's actually true. This is actually a result you can prove, which is that in any network, doesn't matter how big it is, doesn't matter how complicated it is, it doesn't matter how many origins and destinations for traffic you have, as long as all of the edge cost functions have the form ax plus b, so I'm going to call these an affine function. So notice this just generalizes the 1 and 0 and x's that we had before. As long as you have affine cost functions, it doesn't matter what the network is. You are guaranteed that the price of anarchy will never be more than 4/3. Okay? So Brace's paradox and Pigu's examples already witness the largest possible loss from selfish behavior in any one of these routing networks. So perhaps unsurprisingly, we see that there is loss, social loss from selfish behavior. Perhaps surprisingly, in this class of networks, that loss is never greater than 33%. All right, so I don't really have time to tell you about the proof of this theorem, but maybe let me give you kind of a pseudo-argument using a metaphor, an analogy. And for an analogy, I'll use electrical current in electrical networks, a network of resistors. So it turns out electrical current in a network of resistors is actually a special case of this routing model. It's the special case where all of the B terms are equal to 0. So you might have an x over here, a 2x over here, and a 4x over here. The coefficients 1, 2, and 4 correspond to the resistances. So we know a bunch of things about electrical current. So for example, we know we can think of electrical current as an equilibrium if we want. because it equalizes the voltage drop across all paths between two terminals. On the other hand, there's also Thomson's principle, which says we can equally well think of electrical currents as solving a natural optimization problem. Electrical current will find a pattern that minimizes the dissipated energy. And it turns out that when all of these b terms are 0, that dissipated energy is exactly the objective function that we care about, the average travel time. So in the special case where all the b's are 0, what we know from high school physics tells us that the price of energy is actually 1. There's actually no loss whatsoever from drivers behaving in their own self-interest. Now, when the b's are not 0, as we've seen, you do in general have inefficiency. The price of energy can be bigger than 1, but you might hope that it can't break things too badly. And indeed, it's still the case in the general model that equilibria can be regarded not just as equilibria, but also as solutions to a natural energy minimization problem. What's different is that energy function isn't quite the function we care about, the average travel time, but if the cost functions are affine or not too nonlinear, then the two functions are pretty close. So by virtue of exactly optimizing the approximately correct function, equilibria approximately optimize the function we actually care about, the average travel time. Okay? All right, good. Excuse me. So that wraps up the first case study. But before I move on to the second one, bear with me while I digress for a couple minutes. So on this slide is a question which was driving me completely crazy back when I was a graduate student working on this stuff. At that time, I was totally paranoid that I was going to find in the Carpenter Engineering Library at Cornell some 40-year-old dusty journal, maybe in transportation or something, where this 4/3 theorem had already been proven. Right? It was supposed to be one of the main results in my thesis. So I was terrified I'd actually just rediscovered something that had been known for a long time. So I didn't find an article of that form. I still haven't to this day. But still, to sort of mitigate my paranoia, I had to come up with some kind of story, some kind of narrative that might explain why, for some reason, this 4/3 theorem had to wait till the 21st century to be proven. Again, remember, this routing model goes back to 1920, and there's hundreds, if not thousands, of papers written about it in the 20th century. Okay, so why doesn't it seem like this theorem was proved earlier? So the best answer I've come up with to that question concerns a concept called NP completeness, and that concept's also important for our second and third case studies. So let me tell you a little bit about NP completeness. Okay? Actually, let's first talk a little bit about maps. Okay? So as you know, when you look at a continent and the countries are color-coded, they're color-coded such that adjacent countries have different colors, because you want it to be obvious where one of them starts and the other one ends. So a long time ago, when you could actually make a living from printing maps, a relevant question was, how many colors, how many different types of ink are required to be able to color all of the countries so you have no conflicts, so that pairs of neighboring countries always have distinct colors. So you can ask that question about kind of any map. You can ask it, for example, about Europe, or rather, this is a particular subset of 9 countries in Europe. I apologize that France is one of the omitted ones. And you can ask, say, just to color these 9 countries, how many colors do you need? So certainly 1 isn't enough. You'd need at least 2 colors. So the first question would be, could you color these 9 countries red and blue so that each 2 abutting countries have different colors? So here the answer is no, and it's not too hard to convince yourself of that. The 2 colors isn't going to work. For example, you can look at Germany, Poland, and the Czech Republic and observe that each of those 3 countries borders both of the other 2. So just to color those 3 countries, you're going to need 3 distinct colors. More interesting question is, what if I gave you 3 colors, red, green, and blue? Is that enough to color these 9 countries so that you don't have any conflicts? Good. This is trickier, but I see some people already see that the answer is no. So here's one way to argue that the answer is no. One way to do it is to focus on Austria. So all of the countries in this diagram border Austria except for Poland. So that's 7 of them. So we have a ring of 7 countries surrounding Austria. I first claimed that we're going to need 3 colors just to color that ring of 7 countries. And it's actually important for this argument that there's 7 countries rather than 6 or 8. If there's an even number of countries, we could alternate red-blue around them and avoid conflicts. But with an odd number of countries, we need a 3rd color. Otherwise, we get a conflict around the cycle. So 3 colors just for the countries that border Austria. Because Austria borders all 7 of them, it has to have a distinct color from any of them. And so that means we need to use a 4th color for Austria. Okay? 4 colors, in fact, suffice to color this map. There's one way of doing it. In fact, there's a famous result in mathematics from the mid-1970s called the 4-color theorem, which implies that any map can be properly colored with, at most, 4 colors. Okay? So that's the map coloring problem. I give you a map, I give you a target number of colors. Can you or can you not color everybody with no conflicts with that number of colors? Next question I want to ask is, does this seem like the kind of problem we could solve automatically by computer or not? Remember, we talked about Turing's theory of undecidability. We talked how there are problems like the halting problem, which cannot be solved by computer. So could this map coloring problem be another example of an unsolvable problem? Well, you think about it a little bit, you realize no, the answer is definitely not. You at least could, in principle, solve this problem by computer, if nothing else, by using exhaustive search. For example, for this map, you have 9 countries. Suppose you're trying to color it with 3 colors, red, green, blue. 3 choices for each of the 9 countries. So you have 3 to the 9th different options to look at. Okay? So you can just enumerate all of the 3 to the 9 options, see if any of them work. If one of them works, great, you've got your 3 coloring. If none of them work, you can rest assured that 4 colors are necessary. Okay? So that's an algorithm for solving the map coloring problem. How should we feel about this algorithm? Should we be pleased with exhaustive search? Well, if you're only trying to color 9 countries, 3 raised to the 9 options, that's about 20,000. And a modern computer can enumerate 20,000 options instantaneously, pretty much. If you wanted to color the whole world, now you're talking more ballpark 200 countries. So the number of options would now be 3 raised to the 200th power. And that's a big number. It's a really big number. Considerably bigger than the estimated number of atoms in the known universe. So while in principle, a computer could march through all of these possibilities and check for a way to color the countries of the world in 3 colors, that computer program would not terminate in our or anybody else's lifetime. So what's the point? The point is we are not worried about map coloring being an undecidable problem like the ones that Turing identified. However, we might still be worried that while solvable in principle, they cannot be solved in practice, that there is no efficient algorithm terminating in a reasonable amount of time. That is what we are worried about with the map coloring problem. So to turn that worry into a theory brings us to the story of NP completeness. This was developed in parallel on both sides of the Iron Curtain in the early 70s by Cook, Karp, and Levin. And so what NP completeness really is, it's a refinement of Turing's theory of undecidability to exactly identify these problems, which, while solvable in principle, cannot be solved efficiently. That's what NP-complete problems really mean. So there are 3 things I want you to know about NP-completeness. One I just told you. What's the interpretation? If a problem is NP-complete, that means that we don't believe that there is any algorithm that solves the problem that's always guaranteed to be correct and always guaranteed to run in a reasonable amount of time. I say we believe there is no such algorithm because that actually rests on an unproven mathematical conjecture known as the P not equal to NP conjecture, which basically just states that the task of solving a problem from scratch is fundamentally harder than just checking somebody's work. So that may seem intuitive, but it's actually an unproven mathematical statement. But assuming P not equal to NP, there's no guaranteed fast, guaranteed efficient algorithm for an NP-complete problem. Second thing I want you to know is that NP-complete problems are everywhere. There's literally thousands of them that we really wish we could solve, okay? But we can't in general. Map coloring is one example. but there's lots of others. Just figuring out the best way to pack your suitcase for a trip, that's an NP-complete problem. Or trying to schedule classes in a certain number of classrooms, that's an NP-complete problem. And the list goes on. They show up all the time in the real world. The third thing I want to say about NP-completeness is it's important to realize that my primary field, theoretical computer science, has grown up entirely in the long shadow cast by NP-completeness. For 45 years, we have known that there are these thousands of NP-complete problems, problems we really wish we had fast algorithms for, and it doesn't seem like we're going to get them. Okay, so theoretical computer scientists have gotten used to almost never getting what we wanted, never getting a fast algorithm. So naturally, to earn a paycheck, to keep our jobs, we still had to figure out some way to make progress, even in the face of this ubiquitous intractability. And so computer scientists have developed a lot of tools of how to approach NP-complete problems, okay, if you have to solve them. One of the main ways that we do that is through heuristic algorithms. So these are algorithms that are guaranteed to be fast, but are not guaranteed to be correct always, or not guaranteed to be optimal always. For example, for the map coloring problem, you could imagine that there might be a fast algorithm that always uses at most 4 colors to color a map. Now, maybe it's not optimal, because maybe there's some time you could have used 3 colors and it uses 4 instead, but still, that would be a useful algorithm if it quickly always colored everything in 4 colors. That's an example of a heuristic algorithm. And the primary way that we assess the performance of heuristic algorithms is by quantifying to what extent they are close to the optimal algorithm. So we know it's not always correct, so the next best thing would be at least maybe it's always approximately correct. So that led to the idea of an approximation guarantee. And that idea of an approximation guarantee is exactly what drives the definition of the price of anarchy. It's the exact same formalism applied to a totally different thing, right? It's applied to Nash equilibria of games rather than fast heuristics for NP-complete problems. But still, the spirit is exactly the same. So that's the best story I've been able to come up with for why this 4/3 price of anarchy guarantee seemed to have to wait for computer scientists to work on the problem. It seems like just the kind of thing that, culturally is the kind of question that a theoretical computer scientist would ask and most other scientists would not. Okay, so the second case study is going to be kind of a very practical, very real one. This will concern a huge auction, tens of billions of dollars, that ran in the United States in 2016 and 2017, and where computer science played a super important role in its design. Okay? So the story here starts a little more than 5 years ago. Okay, that's when the FCC authorized the design of a novel auction designed to sell licenses for wireless spectrum. Okay, so the items for sale in this auction give whoever bids highest for it gives the bidder the right to use a certain part of the spectrum in a certain location, a certain subset of the United States. Okay? So these spectrum auctions have actually been around for a while, 20, 25 years, but what was different this decade and why they needed a new auction format is that pretty much the entire useful part of the spectrum was already accounted for, had already been allocated to somebody. So in order to give anybody a new license, you had to take it away from somebody else. So that was really the point of this auction, actually to repurpose spectrum, to take it away from people getting relatively low value use for it, and then give it to others who would get higher value use for them. And the spectrum that they targeted in this auction was held by over-the-air television broadcasters. Okay? So frankly, many of which, if they disappeared overnight, it's not clear anyone would notice. Okay? So those are the low-value users. So they wanted to buy back licenses from television broadcasters and then sell them to the highest bidder, which in practice is usually a telecommunications company like T-Mobile or AT&T and so on. So it's really a double auction with 2 phases, a reverse auction and a forward auction. Reverse auction means that the government who's running the auction is in buying mode. So first, the government spends money to buy licenses back from their current owners. And again, their current owners are television broadcasters. Once the reverse phase ends, the second phase is a forward auction where it sells the licenses that it procured to the highest bidder. So these forward auctions are what there's already 20 to 25 years of experience with, but this reverse auction is literally totally new, had never been run until just this started a couple years ago. And this is the part where computer science has had a big role. Okay? So now that the auction has ended, we can kind of see what the numbers look like, and the numbers are big. Okay? So the government spent, this is all in US dollars, the government spent $10 billion buying back licenses from television broadcasters, which is a lot, but it was able to sell them to $20 billion. Okay, so it cleared $10 billion in this auction, which meant that even after covering the auction costs and all that kind of stuff, there was a ton of money left over, which was then applied to the US deficit. That was actually the plan all along, which is probably one of the reasons this bill didn't have much trouble passing a very sort of partisan Congress in the US in 2012. Another reason might be that they chose like a totally veto-proof name for the bill, the Middle Class Tax Relief and Job Creation Act. So I dare you to vote against that. All right, so as you can see, the stakes are high, tens of billions of dollars, and to make spectrum auction design even more stressful, it's actually really easy to screw up. And debacles have happened. One famous one was in New Zealand in 1990. This is before governments really had much experience using these auctions. So back in 1990, New Zealand decided they wanted to create 10 new television channels, nationwide television channels. And so like channels, 4 through 13, something like this. And they wanted to sell, these licenses to the highest bidder. Okay, so it's an auction with 10 items. A given item gives the right for someone to broadcast on, say, Channel 8 throughout all of New Zealand. And for reasons that are sort of lost to the sands of time, they chose an auction format. They chose to sell these 10 licenses using 10 second price auctions, all running in parallel. So what's a second price auction? So second price auction is actually a really good thing to do if you only have one item. Okay, so it should be familiar to you from eBay or from an art auction, something like that. So everybody bids on the item, the winner is the highest bidder, and the selling price is the highest bid by somebody else. So the second highest bid overall. And if you've ever won an auction on eBay, you've experienced this, right? You don't generally have to pay your maximum amount, you only pay high enough to beat out all of the competition. So that's a second price auction. With only one item, it has some really cool properties. Like actually, as a bidder, it's trivial to play in. You have a dominant strategy, which is to just bid your maximum willingness to pay. The auction will basically shade your payment on your behalf optimally after it sees all of the other bids. But the nice properties of a second price auction when you have a single item completely vanish when you run a bunch of them in parallel. Okay, so we're talking about 10 auctions all at the same time. So now a bidder can write down up to 10 numbers, up to 10 bids, if it wants. And so now there's no dominant strategy for the participants. In fact, if you think about it, like put yourself in the shoes of someone who wanted, say, one license, but only one license from this auction. Right? What seems like the right way to go about it, the right way to bid? Like one defensible strategy would be, you pick one at random, like Lucky Channel 7, and you just go all in on that. Another option, which is not crazy, would be to go bargain hunting and bid really low on multiple channels, hoping you get one of them at a bargain basement price. Okay? And a good rule of thumb in auction design is if it's highly unclear how bidders should bid, that's going to be an unpredictable auction and one that's prone to poor outcomes. That's in fact what happened in New Zealand. They were hoping to make $250 million from this auction. So that would be $25 million per channel. Didn't quite work out. They didn't even get 15% of the projected revenue. Okay, they got $36 million. To add insult to injury, in the interests of transparency, the government was required to release not just the selling price of each channel, which remember is the second highest bid, but also the highest bid, making it obvious to everybody just how much money was left on the table. And if you look at those numbers that were released, you can find some pretty cringe-inducing facts. Like, for example, there was one channel where the high bid was $100,000. Now, you already know this is a disaster. They wanted $25 million per. I'm telling you the high bid was $100,000. The second highest bid was 6. Not 6,000, 6. Okay, someone literally got a license in this auction for $6. All right? Okay, so stressful thing if you're actually in charge of putting together these spectrum auctions. So, given that this new reverse auction had to be invented, how does it work? So the format was proposed by a couple economist colleagues of mine at Stanford, Paul Milgram and Ilya Segal. It extends previous formats that have been looked at in the computer science and game theory literatures. And it's called a descending clock auction, and it has a lot of cool properties. One cool property of this auction is that it's really, really simple for the participants. And remember, in the reverse auction, this is where the government is buying back licenses for broadcasters. So the a participant in this auction is a television broadcaster who currently owns a license. Okay? That's who the participants are. So why is it so simple? Well, the auction is going to run in rounds. And in one round, if you're still in the auction, you're going to be asked one yes-no question of the form, would you or would you not be willing to sell your license for, let's say, $1 million? Okay? And you can say whatever you want. You can say no, but if you say no, you get kicked out of the auction forever. What does that mean? That means you're going to get to keep your license, and you will remain on the air. Okay? But you won't get any compensation. Okay? So that's what happens if you say no. If you say yes, you would be willing to sell for $1 million, does not necessarily mean that's what's going to happen. Because it might be that in the next round of the auction, you will be asked another question of the same form with a lower price. Would you or would you not be willing to sell your license for, say, $950,000? And you can either say no and get kicked out forever, or you can say yes and live to see another day. If you're still in the auction when it ends, then in fact the government will buy your license, and the payment will be your most recent, which is also the lowest, buyout offer that you ever accepted. Okay? So that's how this auction works at a high level. Okay? You have buyout prices descending over time, people dropping out once the buyout price becomes unacceptable to them. Okay. All right, so how does the auction end anyways, actually? Well, so fundamentally what this auction is trying to do is it's trying to buy back a target amount of spectrum, a target number of licenses, while paying as little as possible. And a decision that was made very early on in the process was that what it meant to clear spectrum was to clear certain frequencies nationwide. This is so that they could offer national plans to telecoms in the forward part of the auction. So if you want to clear channel 51, it means everybody across the entire United States should be taken off the air on channel 51. So you might, for example, say, let's leave people broadcasting on 38 to 41 and clear 42 to 51. Now, for that to be viable, it was totally crucial that the government used its power to reassign channels of stations that are on the air. So I told you that if you drop out of this reverse auction, you're guaranteed to stay on the air. That is true. You are not, however, guaranteed to retain your channel assignment. It is totally possible you were broadcasting on channel 51 before the auction, and you'll be forced to broadcast on channel 41 after the auction. Okay, so the government did use that power to make this auction format viable. So really, here's sort of what the problem looks like. Here's a picture. So each of these circles represents a television broadcaster. The area of the circle is the broadcasting radius. The color of the circle is the channel. Okay? So you can see that there are 3 channels currently in use in this example. And 3 channels are clearly necessary also for all of these stations to stay on the air, right? Because over here you have 3 mutually overlapping stations. So even them alone need 3 different channels. But you could imagine, maybe you run this reverse auction and maybe you buy back a license, like you buy out that big blue guy. Maybe it doesn't seem like it helped, right? There's still 3 channels in use. But now you can reassign the channels so that only 2 distinct channels get used. And now the brown channel has been freed up nationwide and is available for sale in the forward part of the auction. So that is what this auction is trying to do. Okay? So it's trying to buy out people while spending as little as possible, subject to the constraint that those that were not bought out, those that remain on the air, can be recolored or have new channel assignments that make use of only a target number of colors / channels. Okay? That's the problem that this auction has to solve. Right? Now, I hope you're getting a feeling of déjà vu. This problem is pretty much exactly the map coloring problem we were talking about 15 to 20 minutes ago. okay, of coloring things in a target number of colors to avoid conflicts between neighbors. Once you realize that, you should have a couple of questions for me, right? Because you're like, well, what did I tell you? I told you map coloring is an NP-complete problem. And I told you that NP-complete problems do not admit algorithms that are guaranteed to be fast and correct. But I also told you that somehow this auction needs to solve map coloring problems. Right? So what's going on? How do I explain that? Well, so in fact, this auction does solve these sort of map coloring problems. And it wasn't easy. Okay? So it was a major engineering effort led by Kevin Leighton Brown, who's a computer scientist at the University of British Columbia. And sort of what turned out to be really cool is that state-of-the-art techniques from computer science were sort of both necessary and sufficient to solve these map coloring problems sufficiently quickly for the auction format to be viable. Okay, so just briefly, Leighton Brown's approach was to re-encode these map coloring problems as a different NP-complete problem known as satisfiability. In the satisfiability problem, I give you a big Boolean formula with Boolean variables. And the question is, can you assign the Boolean variables to true and false to make the entire formula true? Okay, that has a lot of practical applications. So hundreds of people have spent decades trying to come up with good heuristic solvers for the satisfiability problem. So Leighton Brown et al. Wanted to leverage all of those great advances on satisfiability solvers to using the repacking problem. That alone was not good enough to get the performance that they needed, so they added some more tricks. They did something which is very common when you're dealing with NP-complete problems, which is you encode additional domain knowledge. You give up on trying to solve the problem totally generally, and you instead focus on the kinds of instances that you actually care about. And because the team knew in advance who were going to be the broadcasters in this auction and what their broadcasting radii were, they had a good a priori sense of what kinds of satisfiability problems they were going to have to solve. And once they encoded that additional domain knowledge, they could get the amazing performance that they needed, meaning solving satisfiability problems with tens of thousands of variables, hundreds of thousands of constraints, typically in a matter of seconds. And I hope the high-level point here is clear, right? So the high-level point is that without techniques from computer science for coping with NP-completeness, the US government could not have run this auction format. They literally would have had to run a different auction in 2016 and 2017. So the third case study is going to be much quicker than the first two. It's going to be a face-off of sorts between Nash and Turing. So we're going to squarely look at the concept of the Nash equilibrium through the computational lens. Let me remind you about Nash's theorem. This was the guaranteed existence theorem, saying in any situation whatsoever, any number of players, doesn't matter what they want, you always have at least one equilibrium. And we talked about how this in some sense seemed like everything that you could want. Okay? Guaranteed existence with no assumptions. Okay, but you might want a little bit more, actually. Because if you think about the standard interpretations of a Nash equilibrium, the reasons why we care about Nash equilibria, most of those interpretations involve somebody, maybe the players themselves, maybe a trusted third party like a mediator, but whatever, some boundedly rational actor has to ultimately compute what people are supposed to do, compute the player's actions at equilibrium. So it'd be really nice if Nash's theorem gave us not merely this abstract promise that an equilibrium exists, and more powerfully gave us a systematic way of deducing an equilibrium, figuring out how players should play. Ideally, we might even want a fast, efficient algorithm for computing a Nash equilibrium. But just in general, we want some kind of constructive version of Nash's theorem. All right, so that's been an open question kind of ever since Nash's theorem, 65 plus years. Okay, and we don't know any constructive version of Nash's theorem. We don't know any fast algorithms for computing one. So what could be the explanation? Well, you should already have a guess at this point, right? We talked about NP-completeness. We said that thousands of natural problems are NP-complete. And we said that NP-complete problems don't seem to have fast algorithms. So a natural first response would just be to guess that computing a Nash equilibrium is an NP-complete problem. Okay? Turns out that's not quite right. This was pointed out by Nimrod Megiddo about 30 years ago. There's sort of a type-checking error between the problem we care about, computing a Nash equilibrium, and NP-complete problems like map coloring. The latter problems are yes-no questions, right? I give you a map, can you or can you not color it with 3 colors? Other NP-complete problems have the same yes-no flavor. What's the yes-no question for finding a Nash equilibrium? We're not asking, does there exist a Nash equilibrium? We know there is one. Nash's theorem tells us that. So the difficulty somehow is only in getting our grubby little hands on this equilibrium that we know is out there. So that's a different character of intractability than NP-completeness, so we needed a new concept. And the solution was given by Papadimitriou. And the proposal is basically, just as we refined Turing's theory of undecidability to talk about NP-complete problems that we really cared about, now we need to refine the theory further. We need to refine the idea of NP-completeness so that it can apply to these equilibrium computation problems. So Papadimitriou said, no, guys, we shouldn't be trying to prove that it's NP-complete. We should be trying to prove a weaker statement, which is called PPAD-complete. Okay, and again, the only important thing to know is that's a weaker, more modest goal than trying to prove NP-completeness, but the interpretations are basically the same. Under an analog of the P not equal to NP conjecture, a PPAD-complete problem we would expect does not have a guaranteed efficient algorithm. You might be wondering about this alphabet soup, like PPAD, what is this? So allegedly, this stands for polynomial parity argument directed version. Christos has tried to swear to me that he was unaware that these 4 letters are 4 of the first 5 letters of his last name. But if you believe that, I've got an offer for you after the talk. So. All right, but it turned out to be a very prescient conjecture, okay, and definition and proposal. It took over a decade, and it took some very difficult, very deep proofs, but we now know, this was last decade, we now know that indeed the problem of computing a Nash equilibrium is a PPAD-complete problem. And again, what's the interpretation? The interpretation is, given the universe as we currently understand it, there cannot be an efficient version of Nash's theorem with the same universal sweep as the existential guarantee that the theorem gives. That theorem fundamentally cannot be made constructive without giving up on universality. Okay? So of course you can apply the same toolbox we use for NP-completeness to PPAD-completeness. You can bake in domain knowledge and try to have an efficient version of Nash's theorem in a restricted domain, and all of that's very interesting. But again, you can't have both. You can't have universality, it seems, and constructive version. All right, so wrapping up. So today I've talked about a few of the many, many points of contact between computer science and economics. These days, there's entire conferences devoted to the research being done on the boundary of these 2 fields. And I really want you to have the impression that the flow of ideas is going in both directions. So initially, the reason computer scientists started learning about game theory and economics is because we needed it. It had the tools that we required to reason about the computer science applications that were emerging in the 21st century. Okay, so we saw one example when we talked about routing in the internet. Another major example, which I haven't talked about, are real-time auctions for online advertising. This actually relates to sort of the motivation for the first problem that Professor Mathieu talked about. So those, by the way, generate kind of the lion's share of the revenue of companies like Google and Facebook. So this collaboration between computer science and economics to have these online advertising auctions is really a major driver behind the internet economy. Okay? A more recent example would be cryptocurrencies. So there it's become increasingly apparent that computer scientists need to think carefully about the incentives that they introduce in their cryptographic protocols that they're proposing. But again, the information also goes in the other direction, with ideas from computer science increasingly influencing the theory and practice of economics. All of our case studies illustrated this point. First, we looked at a 100-year-old routing model, and we saw how approximation guarantees led to new insights, new positive results for this age-old model. For the FCC incentive auction, we talked about how techniques for dealing with NP-completeness were essential for the auction to even be a viable format. And then finally, we talked about how complexity theory, specifically PPAD-completeness, can explain why for 65 years we've never had a constructive version of Nash's theorem. But I guess if you only took one thing away from this talk, I would hope it would be that you have a sense of excitement about the research which is happening at the boundary of these 2 fields. Personally, I'm confident the next 15 years will be just as fun and exciting as the last 15. So thanks very much.